Hey everybody, this is going to be a video explaining Gay-Lussac's law, the combined gas law, and Avogadro's law. So for Gay-Lussac's law, the two variables that we're focusing on here are going to be temperature and pressure. So just like all of the other ones that we were talking about, in order for us to look at temperature and pressure, volume and moles need to remain constant for this gas law. So one of the things for this is if volume is remaining constant, one of the words that we use to kind of explain this is that this is happening in a rigid container. Basically meaning the container that is holding the sample of gas cannot easily change its shape. The other ones that we were talking about where the volume was changing were happening in flexible containers. So like a balloon is a flexible container. It's willing to change its shape, therefore it's willing to change its volume. Gay-Lussac's law needs to be a rigid container, so something that is sealed and rigid and hard. So here's the idea behind this one. So you increase the temperature, okay? Increasing the kinetic energy, therefore the particles are moving faster. If the particles are moving faster and they're in a rigid container, meaning the container is not easily changing its shape, staying in place, if the particles are moving faster, do you think they would collide more or less? More, right? So therefore that is going to be an increase of pressure. And particles are moving faster, they're going to hit each other more if they don't have more space. Simple as that. That's the idea behind Gay-Lussac's law here. And I've got I think it's a cool demonstration to show you of how this kind of plays out. So a really classic example of this, this is not the video I'm about to show you, but a really classic example of this is if you have any like pressurized cans, like hairspray or Febreze or air freshener or spray paint, anything that's like an aerosol pressurized can, there's always going to be a warning label on it that says don't heat this past a certain temperature. The reason for that being is because since it's already under a lot of pressure, if you increase the temperature, the particles will collide even more, increasing the pressure even more, the can has a chance to explode. So that's kind of a real life application of this. Here's just something that's cool. So they are lighting some candles. Remember, that's a combustion reaction, right? So the paraffin wax is combusting with the oxygen in the air. And the candles are sitting in a dish of water, and they just added some blue food coloring to it so it's easier to see. What they're going to do here is they're going to take that beaker in the background, and they're going to invert it on top of the candles. What do you think will happen to the candles? They'll go out, right? Because combustion reactions need oxygen, and so if you are inverting a flask on top of it, it's going to run out of oxygen, and therefore the combustion reaction will stop. Combustion reactions are exothermic. They produce a lot of heat, a lot of energy. So as the candles go out, it's no longer going to be producing any energy, meaning the temperature is going to go down. If the temperature is going down, the kinetic energy is going down, therefore the pressure is going down inside the beaker, right? But the atmospheric pressure, the pressure on the outside of the beaker, is still the same. Atmospheric pressure is remaining constant. So this is what's happening. The reason that the water went up in the beaker is because the atmospheric pressure pushed down on the water, causing the water to go up into the beaker. And the reason it was able to do that now and not before is because the pressure inside the beaker went down because the candles went out, so it got really cold. So just to play this out one more time. Right now, the air around the candles is hot. Particles are moving fast, but it's an open container, right? So the particles are able to move. Now it's about to be a closed, rigid container, so the volume's not changing. As soon as the candles go out, it starts getting really cold in comparison to what it was before. The particles are moving slower. They're not colliding as much, but the pressure on the outside is still greater. So it's because of the pressure differential, the water's coming up. Cool, right? If you've got any kind of clear container at home and candles and water, you could replicate this if you would like to. So looking at our equation here, Gay-Lussac's law is P1 over T1 equals P2 over T2. This is because as temperature goes up and particles are moving faster, they have a higher kinetic energy. If they are in a constant volume, so their space cannot change, they will collide more, therefore pressure goes up. This is another direct relationship here. So here is a question related to that. The gas in an aerosol can is at a pressure of 3 atmospheres and 25 degrees Celsius. 25 degrees Celsius is about room temperature. It's just a heads up. Directions on the can warn the user to not keep the can in a place where the temperature can exceed 52 degrees Celsius or 125 degrees Fahrenheit. What would the gas pressure be at 52 degrees Celsius that causes the can to explode? Let's go. So P1 is the pressure in the first scenario. So that's going to be 3 atm. T1 is going to be the temperature. But remember, temperature always has to be in Kelvin. Biggest mistake. So if it's in degrees Celsius, add 273. So that is going to be 298 Kelvin. It's warning the user to not exceed 52 degrees Celsius. So if that's in Kelvin, we're going to add 273 again. So that's going to be 325. I should do these before I start recording. And we're trying to figure out what that pressure would be. All right. So if we're solving this and we want to solve for P2, we can multiply by 325 on both sides. That causes 325 to go away on this side. And then on the other side, we're left with 325 times 3.0 divided by 298. I'm looking for 2 sig figs on this guy. So I'm getting 3.3 atm for my new pressure. And again, pause. Does that make sense? The temperature went up. The particles are moving faster. An aerosol can is rigid. It can't expand into a larger space. So does it make sense that they would collide more? Yes, that is why the pressure went up. So always pause when you're done with these and just ask yourself if it makes sense. Because I don't trust my calculator, but I trust my brain. All right, here's another one. The combined gas law. As the name implies, we are combining all of the previous gas laws we've learned. Boyle's, Charles, and Gay-Lussac's. So the only thing that is remaining constant in this one is moles. So basically, you have some form of a sealed container of gas, so the amount of gas you have cannot change, but you can vary the pressure, the volume, and the temperature. So it'd be like if I took this balloon and I put it in a brand new room that had a new temperature and a new pressure, and I was curious how the volume would change, like this example problem. So if a balloon with a volume of 1.45 liters at 25 degrees Celsius at 1 atmosphere pressure, so that would be like a normal room, was placed in a room with a temperature of 30 degrees Celsius and 1.50 atm, what would be its new volume? Here we go. P1 is my first pressure, so that is my 1 atm. V1 is my first volume, so that's 1.45. Remember, temperature always has to be in Kelvin. Always. So 25 plus 273, 298 Kelvin. So that would be like room conditions. Like 1 atmosphere is like normal atmospheric pressure, 25 degrees Celsius is room temperature. Our new pressure is 1.50 atm. I don't know what my new volume is. That's what I'm trying to solve for. At 273, 303 Kelvin. So a room that is warmer with a higher pressure. So for this one, there's lots of ways to algebra this. So like you do what you feel comfortable with. Since 303 is on the bottom, I'm personally going to multiply by 303 and then divide by 1.50. That will cause them to cancel out on either side. So I'm going to put 303 on the top over here and then 1.50 on the bottom here. And then I'm just going to type all this in at once. So 303 times 1.00 times 1.45 divided by 1.50 times 298. And so I am getting, did I do that right? Yep. I'm getting a new volume. And it looks like I'm going to get 3 sig figs across the board, 0.983, and this is going to be in liters because it was in liters. All right. So one tricky thing with the combined gas law is you can't really rationalize this because you've got 3 different variables at play. You can't, at least for me personally, with numbers like this, I can't necessarily quickly ascertain, okay, so the pressure went up, so the volume should go down, but the temperature went up, so shouldn't the volume go up? When you got so many variables going on here, you can't really think your way through this one. So you kind of just need to trust your math and kind of go from there. The last gas law is Avogadro's law. I'm not going to spend a ton of time on this. Basically, this one to me just kind of makes sense. If you have more gas, it takes up some more space. That's all it's saying. Remember, Avogadro's number is our 6.02 times 10 to the 23rd, which is equal to 1 mole. So basically, it's saying if you have more moles of gas, it's going to take more space. So, like, for example, let's pretend we've got STP, right? At STP, what does 1 mole of gas occupy? Well, 22.4 liters. So what if I have 2 moles of gas? If I've got more gas, it will take up more space. So that's kind of the idea behind that one. Nothing too fancy with it. So this is another direct relationship. Let's write that down quick. More moles of gas takes up more space. All right, those are all of your basic gas laws.